So in lesson 2.4, we're introduced to the concept of a limit. And so that's what I want to talk about with you in this video. I'm going to introduce the idea of a limit and also the notation that's involved. And then we'll take a look at some techniques for figuring out what the values of limits are. Let's dive right in. So the text talks about indeterminate forms as a way to introduce the idea of a limit. And if you take a look at this function, it's a rational function. It's pretty complicated. And as it turns out, 2 is a value that's not part of the domain for this function. And we see that when you plug 2 in, something weird happens. When you plug in 2 for x and do the calculations, you get an interesting fraction, 0 over 0. In calculus, we consider this an indeterminate form. What that means is, turns out there's no clear answer for what the result of 0 over 0 is. Sometimes it's 5, sometimes it's -4, sometimes it's undefined, sometimes it's 0, sometimes it's 1/3. And what we do is we use this idea of limits to investigate the meaning of this indeterminate form. Let me show you what I mean by looking at some values of x that are very near 2. These table of values from your textbook show us what's happening as we start to move the t value or the x value. My function had x in it, but we're going to look at this t value. We start at 2.5 and the y value is 18, the value of the function. As we move closer to 2.0, look at the values for y. They start moving closer and closer to 16. Now notice we're moving from the right side toward the left. 2.5, 2.1, 2.01, 2.001, 2.0001. I just like saying all those zeros. If we approach from the other side, from the left toward the right, at 1.5 for a value of t, the function is 14. And as we get closer and closer and closer and closer to 2.0, the y values get higher and higher and higher, much closer to 16. It looks like from the right toward the left, we're heading towards a value of 16, and from the left toward the right, we're heading to a value of 16. So that's a pretty good experiment to give us an idea of what we mean by a limit. Remember, I can't actually plug 2 in to figure out what the y value is. 2 is not part of the domain, and it gives me that weird indeterminate form, 0 over 0, when I try to plug it in. Another way to look at this function, and here it is again, is to look at its graph. You'll notice when we graph this function, there is a hole at x equals 2, and that's because we're not allowed to plug in 2. We don't get a y value when we evaluate this function at t equals 2 or x equals 2. So what we do is we look at what's happening from the right and from the left. And we see if it's heading toward a y value. And as you can see, it is heading toward a y value. It's heading toward the y value of 16, just like we showed when we showed you the data in the table. And this concept that we're illustrating here is what we mean by a limit. As you get closer and closer to an x value from the right and the left, as you do that, if you're heading closer and closer to a certain y value, then you have a limit. Then the value of the limit is this y value here. So now let's get a formal definition for a limit, and we'll also introduce some notation. Our definition from our textbook goes something like this. The function f has a limit L as x approaches a, and here's how it's written. The limit as x approaches a of f of x equals L if the value of f can be made as close to the number L as we please by taking x sufficiently close to, but not equal to a. In other words, this is a mathematical way, an English way, to define the phenomenon that we saw either in the graph or in the table. As we moved closer to 2, we were closer and closer on the y-axis to 16. So there's two things that we want to focus on. We want to make sure we understand the idea of a limit, and we also want to start to understand this notation that I've introduced, this thing right here, the LIM. So if we put together our function along with this new notation, we get something like this. And I can already see that I have an error in my presentation. So let me just make a little adjustment here. I am going to turn these t's into x's. And I'm doing that because my original function that I showed you was a function of x. And I also have an x right here. So the way we say this is, we say the limit as x approaches 2, that's this part, of the function 4 times the quantity x squared minus 4 over the quantity x minus 2 is 16. The limit of the function is 16. This guy right here, 16, is our L. That's the value of a limit. So this notation here describes the fact that we're taking a look at a limit, and the value of that limit turns out to be 16. It's not obvious from this algebra, especially since I screwed up and put the t's in there, that the answer is 16. Because when we plug 2 in, we get that 0 over 0. So there must be something else going on here that will lead us to 16. And that's where some techniques of algebra are going to come in. Okay, so I sort of introduced the notation for limits. Let me go ahead and talk about finding limits from a graph. That's one way to find the value of a limit. So here are some tips. We're going to make sure on the graph that the curve approaches the same value, the same y value, from both the left and the right. If you were to see me in person, you'd see me following the graph with my left hand and my right hand index fingers. And if my fingers end up pointing toward the same y value, then that means that limit's probably going to exist. Now, it turns out the actual function does not have to have a value. It doesn't have to equal the limit, and it doesn't have to have a value at all, right? We found that out in our example. There was a hole in the graph, but since it approached the y value of 16 from the left and the right, we still had a limit. Okay. What I want to run through now is a few examples from your textbook, 2, 4, and 6 on page 115, and then 18 and 20 on page 116. So I stole these pictures from page 115, and I want to take a look at finding the limit as x approaches a for each of these functions. And I'll write out the notation after we talk about what's happening. Basically what you want to do is you want to focus on this a value. That's an x value. So we're looking at x equals 1. And we want to see if our curve approaches a particular y value if we follow the curve from the right towards 1 and we follow the curve from the left toward 1. And as it turns out, this function does have a limit because, it's 2 there, because the function approaches 2 from both the left and the right. So the way I write this is, I say the limit as x approaches 1 of our function f of x equals 2. The answer, if you will, the value is 2. Okay, let's take a look at number 4. Again, we're focusing on this a value, so we're focusing on x equals 1. As I approach x from the right-hand side toward the left, looks like I'm heading toward a y value of 3. As I approach x from the left-hand side toward the right, looks like I'm heading to a y value that's about, what, 1.5? Since those numbers are not the same, since these arrows aren't pointing to the same y value, the limit as x approaches 1 for f of x does not exist. And usually what we do is we put a DNE for that. If you're using WebAssign, that's what they're going to ask you to type in. The limit does not exist because the arrow, the y value from the right-hand side is not the same as the y value from the left-hand side. A good way to think of that is if there's a huge gap in your function, then you're probably not going to have a limit. Let's take a look at number 6. I'm going to use the same trick. I'm going to approach a, which is -2, from the left-hand side toward the right and see where that y value is heading. Looks like it's heading toward 3. I approach from the right toward the left, and I'm also heading toward 3. Right, there's my y value. So as it turns out, this limit does exist. It doesn't matter that this dot is way up here. We're not worried about the dot, we're worried about the arrows that I've drawn here. When I do this lecture in person, I say, well, I'm worried about the fingers because I have my fingers tracing that curve. And so since I think I have a limit of 3 here, here's my notation. Limit as x approaches negative 2 of our function f of x equals 3, the y value. Just a note here, the reason I'm writing f of x in each case is they haven't actually given me the expression for these functions. If they happen to give you the expression, for instance, if this one happens to be x cubed plus 1 up here on number 2, then I would go ahead and write that function in instead of f of x. They haven't given me the expression for the function, so I'm just going to use a notation f of x. Hopefully that helps you with these graphs. On page 116, numbers 18 and 20, we're asked to sketch the graph and then evaluate the limit if it exists. Okay, so I'm going to focus on 18 and 20. I'm actually going to cheat. I'm not going to sketch the graph. I'm going to show you how we can get Desmos to sketch the graph for us. Each of these graphs is what we call a piecewise defined function. And what that means is that the function's broken into different parts. So for values of x that are less than or equal to 3, we need to use x minus 1 as our expression. For values of x, I'm going to erase this circle here. For values of x that are greater than 3, we're going to use negative 2x plus 8. And then the interesting question is, what goes on at 3? Is there a limit for f of x as x approaches 3? Okay, so let me show you how we use Desmos to do this thing, and then I'm going to repeat the process for this function here. Notice this function has 3 pieces, negative 2x plus 4, a 4, and an x squared plus 1. So as it turns out, with the Desmos graphing calculator, you can graph piecewise defined functions. The way you do it is, you just type in the function, y equals x minus 1 in this case, and then in braces, curly braces, you put the domain that you want to graph for that part. For us, that's x is less than or equal to 3. So that's this piece of the graph right here, this left-hand side. I did the same thing for negative 2x plus 8, and I only graphed that for x is greater than 3, and that's this piece right here. And then what we're going to do is analyze the graph the same way I analyzed those other pictures. I'm going to look at what's happening as x approaches 3, which is this little point right here. So as I'm coming in from this side, this curve is heading toward a y value. Right there. And as I'm heading toward the function from this side, the curve is heading toward the same y value. Now here's the problem with my sketch. I don't have a number on this grid to tell me what that y value is. But since I know they're heading to the same y value, I can plug in x 3 in for x at one of these spots, I can kind of figure out what the y value is. For the top function, if I plug in 3 to the y value, or the x value, I get y equals 3 minus 1, which we know is 2. And let's just double check it on that bottom function. If I plug in 3 for x here, I get negative 2 times 3, which is 6, plus 8, which is also 2. So even though my graph isn't as accurate as I'd like, it doesn't show all the tick marks for single values, I know the value of this limit is 2 by using a little algebra. I check and see that the top function and the bottom function are both heading towards the same y value. So the way I would write this is the limit as x approaches 3, which was our interesting point, a equals 3, of f of x equals 2. That's number 18. So here's the graph of number 20. Remember we said it had 3 parts. For x is less than 1, we're going to use negative 2x plus 4. For x equals 1, we're going to use the y value of 4. And what that is basically saying is we want the point 1, 4 to show up. Notice it shows up as this little dot right here. And then for x is greater than 1, we're using x squared plus 1. Now remember from our other graphs, we're not going to panic if that dot is not on the tip of this sort of point here. All we want to do is investigate what's happening as we approach the x value of 1 here. So from the left, it looks like I'm heading to a y value, which is right here. Oops, that's not even close. The y value is about right here. And from this side, it looks like it's heading to the same y value. Don't worry about the dot, just worry about where these two curves are heading. Again, my graph's not very accurate, so I don't know exactly what the y value is. So what I'm going to do is I'm going to use a little substitution again. I will figure out the y value for x equals 1 on the top function, negative 2 times 1 plus 4. And it looks like, again, this is a value of 2. And I'll do the same thing for the bottom function, the bottom curve, the blue one. I get 1 squared plus 1, and lo and behold, that is also 2. So just like the other problem 18, this problem 20 has a limit as x approaches 1, which is the interesting point in this function, a equals 1. The limit as x approaches 1 of f of x turns out to be 2 again. So that's the idea behind those types of problems. Plus, we got to learn how to do piecewise functions on Desmos. So hopefully this was helpful. Let's continue. Even when you have a nice graphing tool like Desmos, graphing is not the most efficient way to investigate limits. We have some algebraic techniques that are going to make this thing a lot easier. First of all, we have constant functions, and the limits of constant functions are very easy to calculate. Our rule is, and I'll kind of write it in right here, that the limit as x approaches some number a of a constant function, usually we write something like k here, the limit as x approaches a of a constant function is that constant. So for example, if they give us the limit as x approaches 7 of the constant 5, the answer is 5. Right? This is a horizontal line. All of the y values are 5, so every limit on this function is 5. And that's the point for constant functions. So don't panic when you see like a 5 or a 6 or a 12. Those functions are easy because the answer is just whatever that constant is. The value of the limit, I should say, is that constant. Another great technique that I've highlighted in red here is substitution. If you have a function where there are x variables, you can take the number that x is approaching, which we usually call a here, and you can plug it into the function and see if you get an answer. If you get an answer, we're in great shape. Unfortunately, we also sometimes end up with those indeterminate forms, like 0 over 0. And when you get an indeterminate form, you have to try something else. Usually, the trick of factoring and canceling is going to help us. And I'm going to show you some examples in a second on that. Once you've factored and canceled some things out, then you go back and you just try substitution again, and usually it works out. And then finally, as a last resort, you can always graph the functions like we did with Desmos and see if you can figure out from the graph what the limit is. Let's try some algebraic limits. So I want to work through several of these problems here. Page 116, 24, 34, 40, 50, 54, and 60. 54 is pretty interesting. That's why I put the question marks next to it. Okay, so we start out with number 24, which just says the limit as x approaches negative 2 of negative 3. That's a constant function. So like we said, the answer is just negative 3. The value of the limit is negative 3. Every y value of the constant function negative 3 is negative 3, so the limit must be negative 3 when x approaches negative 2. Enough said on that one. Let's look at 34. 34 is more interesting. All right, we've got a rational function. We're taking the limit as x approaches 1 of x cubed plus 1 over 2x cubed plus 2. What I want you to know about this is you always want to try substitution first. Okay? If you have an expression that has x's or a's or whatever your variable is, try substitution first. What that means is I'm going to plug 1 in for the x's and see what happens. So when I do that math, I get 1 cubed plus 1 in the numerator, and on the bottom I get 2 times 1 cubed plus 2, and all I'm going to do is see what that equals. So on the top I get 1 plus 1, which is 2. On the bottom I get 2 plus 2, which is 4. That's 2/4. Always reduce your fractions. So the value of this limit is 1/2, the y value. Again, if substitution works, just use it. No problem. Okay, let's take a look at number 40. Continuing with our examples here. Problem 40's got all kinds of crazy stuff. The limit as x approaches 3 of the function x square root of x squared plus 7 divided by 2x minus the square root of 2x plus 3. Okay. Again, the first thing I'm going to try is substitution. So I'm going to put 3's for all the x's. So I get 3 times the square root of 9 plus 7 over 2 times 3 minus the square root of 6 plus 3. And, some good things happen here. The square root of 16 is 4, so I have 3 times 4, which is 12 in the numerator. On the bottom, 2 times 3 is 6, and the square root of 9 is 3, so that's 6 minus 3, which is 3. 12 divided by 3 is 4. Whew, we lucked out. The value of this limit is 4, and all I had to do was plug the 3 in to find it. So, it sounds like substitution is going to be a good way to go. Unfortunately, what happens is we run into some weird things like indeterminate forms, and so now we need to talk about some of those. As I mentioned, there were some other problems I wanted to do, like 50. All right, let's take a quick look at 50. I guess I'm writing in red now. For 50, it says the limit as x approaches -2 of x squared minus 4 over x plus 2. If I try substitution here, something weird happens. On top, I get 4 minus 4, which is 0. And on the bottom, I get -2 plus 2, which is also 0. This is an indeterminate form. And what that tells us is we have to try something else. So in the slide with the notes, I mentioned that you can try the trick which we call factoring and canceling. So instead of doing the limit in this form, I can do the limit as x approaches -2, and I can factor my function. Notice on top we have a difference of perfect squares, and hopefully you remember that those factor as x minus 2 and x plus 2. This one factors as x minus 2 and x plus 2. And on the bottom I still have that x plus 2, and that is also a binomial. Now here's what's cool about this. I can just use algebra and I can cancel these things out. Okay? And when that happens, I have a new limit problem which is very easy to use substitution on. The limit is x approaches -2 of x minus 2. Now when you do substitution, you do not get an indeterminate form. You get -2 minus 2, which is -4. So what I want you to notice is that this indeterminate form 0 over 0 turned out to be -4. When we had an indeterminate form at the beginning of this video, it turned out to be -16. And that happens. So don't panic. When you get 0 over 0, you're just going to have to try something else. Usually factoring and canceling is going to work for us. So please try that. And then again at the bottom here, we just substitute. Okay, I mentioned that we wanted to talk about 54. And 54 is also kind of interesting. This time we're looking at variable b instead of variable x, and b is heading towards -3. And my fraction, or my rational function, is b plus 1 over b plus 3. Okay, now when I do substitution on this problem, we also get something interesting, but it's not an indeterminate form. When I plug -3 in on top, I get -3 plus 1, which is -2. when I plug it in the denominator, I get 0. Negative 2 divided by 0 is not an indeterminate form. Okay, something else is happening here, but it's not a y value. There is no value for this limit. We're going to learn later how to investigate what's happening at this undefined value. But for now, we're just going to say that the limit does not exist. Okay, we might be heading towards something, but it's not a number. Okay, what's happening here is there's an asymptote. And so we're heading either toward a really large value or growing without bound, infinity is usually what we call it, or we're going to negative infinity, so it depends. My point is this. If you get a division by 0 where it's not 0 over 0, where it's negative 2 over 0, 5 over 0, 12 over 0, that limit does not exist. It's not an indeterminate form. Factoring won't help us. Okay, let's take a look at our last one, which is 60. And 60, I wanted to show you because there's a weird factoring situation. It's doable, but you have to really want to see it. So I'm going to help you out on it. It says x minus 4 over the square root of x minus 2. And even though it doesn't look like it, we can factor this numerator in the same way that we did problem 50. This is also a difference of squares, but when you factor it, the square root of x, if you will, is the square root of x. So this factors as the square root of x plus 2 times the square root of x minus 2, that numerator. We still have the square root of x minus 2 on the bottom, and we're still doing a limit. And so as you can see, these two binomials will cancel. And now I can just do substitution like I did before. And this is going to end up being 2 plus 2, because the square root of 4 is 2. So 2 plus 2 is 4, and I do have a value for this limit. Let me point out that I forgot to do this, but up here, when I plug 4 in to begin with, I do get an indeterminate form. I get 4 minus 4, which is 0, over square root of 4, which is 2, minus 2, which is 0. Don't do the factoring trick unless you have an indeterminate form. All right? If you can just plug it in and get an answer, you're done. You could stop. Or if you get a negative 2 over 0 or something like that, you can stop and say does not exist. So I only went through this factoring process because I ended up with that 0 over 0. Okay, so we've covered a lot with these limits. I appreciate you hanging in there. I do want to talk a little bit about limits at infinity. Okay, and as this slide shows us, we're interested in the behavior of a function as x grows in absolute value without bound. It's either going to get very positive or very negative. So we're talking about the far right-hand side of the coordinate plane or the far left-hand side of the coordinate plane. In this case, our main tool is going to be 1 over x, or 1 over x to the n. And I'll show you what I mean by this in a minute. It turns out that particular function goes to 0 when x goes to either positive infinity or negative infinity. And this 1 could actually be any number. I'm going to show you why that's true. The value for our limit may be a number, or it may be infinite. And that's a tricky statement because infinity really isn't a value. It's the idea that something grows without bound. Okay, let's talk about what I mean by 1 over x. In this graph, I use Desmos to graph several functions. My first one is simply 1 over x. That's the red guy. And then I also graphed 4 over x, which is the blue one, and then I graphed 12 over x, which is the green one. And what we mean by limits at infinity is we look to see what y value our curves are heading toward as we move way far out on either the positive x-axis or the negative x-axis. We look to see which y value we're heading toward. And I think you'll agree that for all three of these functions, our y value that we're heading toward happens to be the x-axis. There's an asymptote there. So we would say that these limits, as x goes to infinity, are equal to 0, right? 0 is the y value for the x-axis. All right. So for example, the limit as x approaches infinity for 1 over x is 0. When I put an infinity in here, 1 over x goes to 1 over some really, really huge number, and that basically is heading to 0. The same is true for the limit as x approaches negative infinity of 1 over x. We head to 0. In fact, I could rewrite these statements with 4 over x or 12 over x or 72 over x or 150,000 over x. If there's a constant on top and the variable x or some power of x on bottom, that thing's always going to go to 0 as x goes to infinity. And this picture kind of shows that there's an asymptote out here on either end, and we're heading towards these y values of 0. And that tool is going to help us solve some interesting limits. So I want to wrap this discussion up with a few examples. I'm actually going to start with number 75, even though it's not on my list. This is on page 117, number 75. The problem shows the limit as x approaches negative infinity. Oops, that's negative 8. Come on, man. Of a rational function which has a polynomial over a polynomial. We have 3x cubed plus x squared plus 1 over x cubed plus 1. And the trick I want to demonstrate for you is that when we have a rational function like this with two polynomials, one in the numerator, one in the denominator, what we want to do is we want to multiply the top and the bottom by 1 over the highest power of x. And what I mean by that is I'm going to multiply 1 over x cubed on the entire numerator, and I'm going to multiply by 1 over x cubed in the entire denominator. When you distribute this, right, don't forget you have to distribute, you get a new fraction, which looks something like this. The limit as x approaches negative infinity of 3, because 3x cubed times 1 over x cubed is 3, plus 1 over x, because x squared times 1 over x cubed reduces to 1 over x, plus 1 over x cubed. In the denominator, we get 1, because x cubed times 1 over x cubed is 1, plus 1 over x cubed, because 1 times 1 over x cubed is 1 over x cubed. And then now we're going to sort of do a little substitution. I'm going to send x to negative infinity for this fraction, and this fraction. And when I do that, I already showed you on those graphs that every y value heads towards 0. 1 over x heads to 0. 1 over x cubed also heads to 0. And so what we end up with is those fractions disappear because they go to 0. And I end up with 3 divided by 1, which is 3. The value of this limit is 3. Now that we've run through that process, I'm going to tell you a little secret. Anytime you have polynomials where they are the same degree, meaning the largest power of x is the same, and you're going to infinity or negative infinity, everything's going to go away except the leading coefficients. So notice we ended up with the 3 and the 1, and that's what the coefficients were. There's a 3 on top and a 1 on bottom. So that trick will work. If you're not comfortable with that, you can try my 1 over x cubed thing. Now let's talk about 74, 76, and 78. Okay, so I tried to save some time here. I've got these things written out ahead of time. Remember, my trick is to find the highest power of x and multiply the numerator and the denominator by 1 over that power. So for this problem here, I'm going to multiply by 1 over x squared on the top and 1 over x squared on the bottom. I'm allowed to do that because I'm really just multiplying by 1, right? This is what we call a form of 1. It's a weird looking form of 1, but when the numerator and the denominator are the same, I'm just multiplying by 1, which does not change the value. Okay, so let's go ahead and do that. And you'll see that on top, I end up with a new limit, which is x is going to negative infinity still. My handwriting is deteriorating as this video moves on. I end up with 4 minus 1 over x squared over 1 over x plus 2 over x squared. Okay, now I'm going to, quote unquote substitute negative infinity in for these fractions, and we get a problem. This guy's going to turn into 0, this one's going to turn into 0, and so is this. So the value here, if you will, turns into 4 over 0. That's not an indeterminate form, right? That's an undefined division. So the answer, if you will, for this one is dne. This limit does not exist. Okay, let's try the same trick on the next problem, 76. I'm going to look for the highest power, which is x to the 4th. So 1 over x to the 4th. 1 over x to the 4th. Basically, I'm dividing every term by x to the 4th. And when I do that, I get a new limit. X is going to positive infinity, which actually doesn't really make much of a difference to us. And look what happens. I get 2 over x squared plus 3 over x cubed plus 1 over x to the 4th divided by 1, because x to the 4th times x to the 4th is 1, minus 1 over x squared. All of these fractions turn into zeros. So this is interesting. This time I get 0 over 1. That's not an indeterminate form either. That's just 0 divided by 1, which is 0. So the value of this limit is actually a y value, which is 0. It's not dne. That's good news. And then finally, if I multiply, ooh, wait a minute. Remember the trick I pointed out to you before? Look at the highest power. They're both x to the 4th. So basically, all these guys are going to turn into 0 when I do my trick. And these things are going to cancel out. And so I can see right away this is just going to be 4 over 2, which is 2. So that's a little trick. If the degree of the polynomial in the numerator and the denominator are the same, you can just get rid of everything and look at the leading coefficients. If you don't like that trick, go ahead and multiply by 1 over x to the 4th, and you will arrive at the same value. So for 74, it doesn't exist because I ended up with 4 divided by 0. And the trick on that one is the highest power was on top, x squared. For 76, I ended up with 0, and that's because the highest power was on bottom, x to the 4th. For 78, I ended up with the number 2 because the numerator and the denominator had an equal highest power, an equal degree. So I look at the leading coefficients and I get 2. Okay, I dumped a lot on you in this video. Hopefully this helped clear up some of the reading from the text, but as usual, you're welcome to email questions. Good luck.